If you're provided with 18,2 grams of potassium nitrate, how many potassium ions would be in that sample? So first let's work out how many potassium nitrates would be in that sample before we try and get too exotic and work out what the ions are. So I'm first going to work out the molar mass of potassium nitrate. I need to know what potassium nitrate's formula is. And the way that I do that is I say potassium has a valency of 1 because it's in group 1. Nitrate is NO3, and you're expected to know this now. And it has a valency of 1, so it's KNO3. And the molar mass is therefore 39 plus 14 plus 3 times 16, and that turns out to be 101. Number of moles is equal to mass over molar mass, 18,2 divided by 101, and we land up with 0,18 moles. Now, for every 1 potassium nitrate, I would have how many potassium ions? It turns out in this case it's a 1-to-1 ratio. But let's say I'd had magnesium nitrate, I would have 1 magnesium for 1 magnesium, but there would be 2 nitrate ions, and so it would be a 1-to-2 ratio if I was working out the nitrate ions. So just be aware what the ratio is in there. And then what we're going to say is, therefore, if I have 0,18 moles of potassium nitrate, I would also have 0,18 moles of potassium ions. The question is how many ions are there? So number of particles is equal to number of moles times Avogadro's constant. So I take that 0,18, I multiply it by 6,02 times 10 to the 23, and I land up with 1,08 times 10 to the 23 K plus ions. Next one, a solution of magnesium sulfate is known to have a concentration of what is given there. Write a chemical formula first for magnesium sulfate. Magnesium has a valency of 2. Sulfate has a valency of 2. So it becomes MgSO4. What mass of magnesium sulfate is present in 50 centimeters cubed of that? So you first work out the number of moles. And number of moles is equal to concentration times volume, which is equal to 0,04 times 0,05. Why 0,05? Because I made that 50 centimeters cubed into decimeters cubed, and I land up with 0,002 moles. But that wasn't the question. The question was mass. Mass is then number of moles times molar mass, 0,002. Don't forget to leave these numbers in your calculator. And then I need the molar mass of magnesium sulfate. And that is going to be equal to magnesium, which I think is 24,3, 32 for sulfur, 4 times 16, which is 64, and you get 120,3. And your answer turns out to be 0,241 grams. Then it says, what volume of that solution would be required to make up 500 centimeters cubed of another concentration in a volumetric flask? So this is your dilution thing, where the first thing you do is you say, what do I know quite a lot about? And I know quite a lot about 0,25 moles per cubic decimeter and 0,5. I can get a number of moles from that. Number of moles is equal to concentration times volume. 0,025 multiplied by 0,5 decimeters cubed, and my number of moles is 0,0125. So that's how many moles are in the solution that I am going to make. But where did I get them from? I got them from this solution. So I'm going to look for the volume. Volume is going to be equal to number of moles divided by concentration, and the number of moles is going to be 0,0125 because that's all the moles I need, and there's a concentration of 0,04 divided through, and I find I need 0,312 decimeters cubed, which is the same, by the way, as 312 centimeters cubed. And if you think about it, you could then put 312 centimeters cubed, top it up with water in a volumetric flask to 500 centimeters cubed, and you will have diluted that solution from being a 0,04 mole per cubic decimeter solution to being a 0,025 mole cubic decimeter. So this is a standard, they keep asking if people get it wrong. They may say how much water needs to be added to, or something like that, and you would need to work it out and then relate it along the way. Next one, name a molecule that has polar bonds but is a non-polar molecule. There are a few of these that you can do. One of them is your tetrahedral shaped molecules. The other ones that you could easily enough do is also something like carbon dioxide. Carbon dioxide, non-polar molecule because it's linear and symmetrical. But our very typical ones are the methane, or carbon tetrachloride, or carbon tetrafluoride. All of those have got polar bonds but turn out to be non-polar molecules because of the symmetry of the molecule. Study the substances below and select one which meets the criteria of each statement. So first we want to see what has got polar covalent molecules. Let's think about it. Ammonia is nitrogen and hydrogen, both nonmetals, and they have an electronegativity difference, so that's a polar covalent. Let's just check the rest. Carbon, we get carbon coal, we get carbon diamond, we get carbon graphite, we get carbon Buckminster fullerene. So all of those are atomic lattices, and they are the whole lattice is covalently bonded. So that's not a polar covalent molecule because they have the same electronegativity. Lithium is a metal, bromine is a nonmetal, and therefore lithium bromide is ionic, and carbon tetrachloride is going to be, as we discussed earlier, has polar bonds but is a non-polar molecule, so that is not polar covalent. So our correct answer there is going to be ammonia. In the solid and liquid phase, the molecules are held together by hydrogen bonding. Now, hydrogen bonding exists in three main molecules: hydrogen fluoride, water, and ammonia. So ammonia would be your answer. By the way, alcohol molecules with the OH group hanging off the end also gets weak hydrogen bonding type forces, and that may be asked in an organic question. The next one is a solid allotrope comprises of an atomic lattice of covalently bonded atoms. We just talked about the fact that carbon is covalently bonded completely and that it is through the entire lattice. So it's an atomic lattice of covalently bonded. So carbon is your correct answer there. Dissociates into ions. There's only one ionic substance there, so lithium bromide is your correct answer. And conducts electricity when melted into a liquid, but not as a solid. That is characteristic of any ionic substance, and so lithium bromide is the answer there too. We've got a Boltzmann distribution curve here, and it illustrates the relative distribution of energy in a given sample at two different temperatures, T1 and T2. Which of the two graphs represents the energy distribution at the higher temperature? Briefly explain. Now we tend to go, oh, higher temperature, must be this one, this peak is higher. No. That's number of molecules with a certain amount of energy. Here, lots of molecules have got hardly any energy. Few molecules have got lots of energy. That's cold. When lots of molecules have got lots of energy, that is hot. So T2 is got at a higher temperature than T1. Why? Because the area under T2 at higher energies is greater than the area under T1 at higher energies. Or you could have said the area under T1 at low at least at low energy is great, therefore it's a low temperature. So those are the kinds of questions that can be asked around these Boltzmann distribution curves. Now we've got zinc and nitric acid, and they form zinc nitrate and hydrogen, and then you've got delta H is less than 0, so that's negative, so that's an exothermic reaction. We then get asked 10 grams of zinc granules is placed into a flask, and then 100 centimeters cubed of nitric acid of concentration given to me like that is added. The mass of the flask and its contents are then measured at regular intervals. What are we going to do with that? First thing we do is they ask me to draw a graph of y versus x, mass of flask, you could have said in kilograms or in grams, I don't mind, and versus time. What's going to happen? At first, there's going to be a lot of mass. What gets given off in this reaction is some hydrogen gas. So this flask will steadily get lighter and lighter and lighter. So the mass is going to steadily decrease because hydrogen is being sent off into the atmosphere until it stabilizes at the end. So that is our graph that they're asking for. What is the dependent variable in this experiment? In other words, what am I measuring? I'm measuring the mass of the flask in grams. Explain why this reaction is not an equilibrium reaction. It is an open system. It was placed in a flask, not in a sealed container, not in a pressure vessel, just in an open flask. So we're losing the hydrogen all the time. So it cannot reach equilibrium unless it's a closed system. What is indicated by the portion of the graph that is parallel to the time axis? Completion of the reaction. Use calculations to determine the limiting reagents in this reaction. So now we need to take a look at our equation. We need to see how many moles of each we've got. So I'm going to start by seeing how many moles of zinc I've got. And I'm going to go number of moles is equal to mass over molar mass, which is equal to 10 divided by 65,4. And that's equal to 0,15 moles. Then, in terms of the nitric acid, I am going to say number of moles is equal to concentration times volume. Concentration 0,65, volume 0,1, and I land up with 0,065 moles. Now I need to relate these two to one another. I didn't, by the way, use this 2 yet. I'm only going to use it in a mole ratio, and there's an invisible 1 over there. So, what shall we do? We're going to say zinc is to nitric acid as 1 is to 2. Therefore, 0,15, I'm going to require 0,3. I do not have 0,3, so that will not work. If, on the other hand, I said zinc is to nitric acid, and its 1 is to 2, 0,065, zinc is to nitric acid, is to 0,03, I do have enough. So, therefore, the nitric acid is my limiting reagent. Use calculations to determine the limiting reagent. What volume of hydrogen gas is produced in this reaction? I then must use the number of moles from the limiting reagent in doing my further calculations. And I am going to say nitric acid relates to hydrogen as 2 is to 1, 0,065 is to 0,0325. Volume is equal to number of moles times molar volume. I've now got 0,0325. Remember, this was from the balancing numbers over here. Those were your balancing numbers in your original equation. Molar volume is 22,4, and therefore you land up with 0,728 decimeters cubed. On to the next thing, which is to establish, what if I make these changes? 10 grams of zinc dust instead of zinc granules. Well, zinc dust is obviously going to go faster. So that would be more or less what that would look like. The acid is heated to a temperature of 40 degrees before being added. Well, that's also going to go faster. So it will also look pretty much like the pink curve. Boom. And then they're going to say, you can't decide which of those is quicker and which one's slow. I'm happy with them both, just looking like they clearly lose mass more quickly at an earlier time than the previous one. 50 centimeters cubed of acid of the same concentration. Now remember, we've talked about adding volume to something. Here's my vessel. Here's some zinc. I put 50 centimeters cubed of a certain concentration or 100 centimeters cubed of a certain concentration. My reaction sites are over here. Makes no difference if I've got extra volume or whether I have not got extra volume. And so it is important to realize that there is going to be no change. In other words, the blue line will look exactly the same.